Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving beam deflections by integration of the second-order beam differential equation. The next example is a simply supported beam with an applied end moment. We're asked to evaluate the equation for the deflection, sketch the deflected shape, and find the peak deflection and where it occurs. I actually like to start by sketching the deflected shape. I note that because they have simple supports at the end, both ends are going to rotate, and this downward moment is going to cause the beam to rotate sharply in that direction, and then it's going to follow through to the other side, something like that. Okay. The important thing here is that the maximum deflection, I don't know exactly where it occurs, but I will deduce, because of the strong moment at the right end, the maximum deflection is going to occur somewhere to the right of center. So let's write that as Vmax at x equals we're not sure. Okay, and the reason I chose this problem is because I want to illustrate the method for finding the maximum deflection when we don't know exactly where it occurs. First step in the solution is to identify the moment function. We need to solve for the reactions. If you need to draw a careful free body diagram to do this, please do. I'm going to take a little shortcut here by noting that my applied moment in the clockwise direction can be resisted by a couple in the reactions applied in the counterclockwise direction. And the value of each reaction is going to be m0 over L. This basically always occurs for a concentrated moment anywhere on the beam. It doesn't matter where it's applied. So the next step to evaluate the moment function, we'll make a cut somewhere in the beam. We'll draw a free body diagram of the beam to the left of the cut. We'll add in the reactions and loads. All we have here is a reaction of m0 over L. The distance to the cut is x. Then we have our moment function, m of x. And summing the moments at x, we get m of x plus m0 over L times x equals 0. I'll flip the sign. m0 over x equals m of x equals m0 over L times the distance x, and that's it. That's our moment function. Step 2, sorry about that. Step 2 is the boundary conditions. Okay, our boundary conditions, we have a pin at each end. At each location, we know that the deflection, not the rotation, but the deflection equals 0. We write those boundary conditions. V of 0 equals 0. That means V at x equals 0 is equal to 0. And then V at x equals L is equal to 0. We must clearly identify the locations where the boundary conditions apply. Step 3 is to integrate. So let's summarize the equation that we need to integrate. The second order beam equation, d squared v by dx squared, with an EI out in front, equals the moment function, in this case, m0 over L times x. Start a new sheet here. We have our boundary conditions. We'll integrate once. EI dv by dx equals negative m0 over L times x squared over 2 plus a constant of integration. We'll integrate again. EI times v of x equals negative m0 over L times x cubed over 2 times 3 is 6 plus a c1x plus a c2. Now we can apply our boundary conditions. The first one, v of 0 equals 0. First term is 0, second term is 0. So we're left with c2 equals 0. So that implies that c2 must be equal to 0. Now we'll apply this second boundary condition. V of L equals 0. We have negative m0 over L times L cubed over 6 plus c1 times L. Set that equal to 0. Simplify the first term a little bit. I have m0 L squared over 6 plus c1 L equals 0. that tells me that C1 is going to be equal to, flip the sign, m naught L squared over 6 divided by L, m naught L over 6. Okay? So in summary, V of x equals, I'm going to divide through by EI. I have negative m naught over L EI times x cubed over 6 plus C1 m naught L over 6 EI times x. Normally I don't do this, but to make it a little bit easier to work with, I'm going to simplify this by pulling out an m naught over L EI, and I'm left with m naught over 6 L EI actually, and I'm left with x cubed, negative x cubed plus L squared x. Okay, I'm going to leave it in that form. So skipping to the next page, that's what we have. M naught over 6L, look, I forgot my EI. M naught over 6L EI times negative x cubed plus L squared x. Okay, so now we need to evaluate the maximum deflection. We don't know where it occurs, but what we do know is that at the location of the max, the derivative, or the rotation, is equal to 0. So we'll use that as a basis for finding the location. Let's write dv by dx equals, solve for dv by dx, set it equal to 0, solve for x, and then we'll evaluate the deflection there. It's equal to m naught over 6L EI. What I really care about is this term here, negative 3x squared plus L squared. I'm going to set that equal to 0. That tells me that x squared equals L squared over 3, or x equals plus or minus L over root 3. So only the positive root makes sense. We'll conclude that x equals L over root 3 is the location where the maximum occurs. Now to evaluate it, we'll evaluate V at L over root 3, which equals m naught over 6L EI times negative L cubed over root 3 cubed plus, going from this equation up here, L squared times L over root 3. Okay, I'm going to factor out the L cubed here so I can work with the numbers in between. I have an L cubed over L gives me m naught L squared over 6EI. Then I have negative 1 over 3 root 3 plus 1 over root 3. Okay, so this, just working with the numbers in here, reduces to, I'm going to factor out the 1 over root 3. I have a negative 1/3. 1/3 plus 1 is 2/3. So I have 2 over 3 root 3. Okay, and then multiply that by the 1/6 out here. That means this is going to reduce to a 3. So I have 1 over 9 root 3. Here's our answer, m naught L squared over EI times 1 over 9 root 3. That is the maximum deflection. And it is positive as we determined from our sketch. So that concludes this example.